Last time we talked about the test for independence. And a test for independence is used to determine whether two variables are related or not. An example we talked about was whether handedness, whether you're left-handed or right-handed, whether that's related to your cell phone ear preference, which ear you prefer to hold up your cell phone to. Notice that both of those variables are qualitative variables, right? If I ask you which hand is your dominant hand, you would answer with a word, either right or left. And if I ask you your cell phone ear preference, you would answer with a word, right, left, or no preference. So both of those are qualitative data. The test for independence is used to determine whether two qualitative data are related or not. Today we're going to talk about how to determine whether two quantitative data are related. So these are going to be the numbers. So before I do that, let me introduce the term bivariate data. Bivariate data just means that we're going to collect two pieces of data from each individual. For example, I can ask each person their age and their height. And usually we're going to pair them up as an ordered pair, like XY coordinates. The main type of graph for bivariate data is going to be a scatter plot. Here we're collecting for each student their absences and their grade. So each pair represents data for one student. So this student had 8 absences and their grade is 82. This next student had 2 absences and their grade is 92. So typically, first column will plot on the x-axis, second column will plot on the y-axis. On the x-axis, I want to put my absences. And my absences go all the way up to 15. Let me count by 1 here. And then on my y-axis, I'll put the grade. And I think I have this set up so that every 2 marks is 10. And then each pair we're going to plot as XY coordinates. Okay, first student 8, 82, 8 on the x-axis, and then we're going to go up 82, and then make a dot. Next, 2, 92, 2 on the x-axis, and then 92 up, and then so on. And that's a scatter plot. So don't worry about drawing this by hand. We're not going to draw this by hand. We're going to actually use R. And here are the commands in R that we'll need to make a scatter plot. So let me switch over to R and show you how this works. All right, I'm going to demonstrate using regular R, but if you're using the online R console or R Studio Cloud, it should work exactly the same. The first thing we need to do is enter our data, our 2 columns of data. And we need to decide on a name for each of those columns. It doesn't matter what you name it. First one was absences, so let me just call it absences, equals C parentheses. And then you're going to type in the data separated by commas between the parentheses. Our absences were 8, 2, 5, 12, 15, 9, 6. So here I'm typing it in by hand, but on your lab I have it set up to where you can just copy and paste the data between the parentheses. Our next column was grade. Let's call it grade. Equals C parentheses, and then we'll type in the data separated by commas. My grades were 82, 92, 90, 51, 43, 70, 82. Once you have the data entered, to make a scatter plot, the command is plot, P-L-O-T, parentheses, and then you're going to type in whatever name you pick for the X and whatever name you pick for the Y. So we picked absences for the X, so type in absences, comma, and then whatever name you pick for the y. Here we pick grade, and then hit enter. And there should be a pop-up window with the scatter plot. Notice that in our hand-drawn scatter plot, and also the one that's drawn in R, the points line up almost on a line. So when that happens, we want to draw the least squares regression line, or the line of best fit. So this is basically just the line that's closest to all of the points. So before I talk about how to get that line, let's take a step backwards and talk about lines in algebra. So in algebra, you may have remembered that the equation of a line is y equals mx plus b. And there's two important numbers here, the m and the b. The m, which is the number that's multiplying the x, the coefficient of the x, that's the slope. The other number that doesn't have an x attached to it, the constant, that's the y-intercept. This equation up here, I just wrote there because in statistics, you may see it written like this, which is the same thing. In this form, which number is the slope and which number is the y-intercept? Okay, the slope is the number that's multiplying our x, which is going to be the b1 here. That's our slope. And then the other number, the one that doesn't have an x attached to it, which is the constant, is the y-intercept. Okay, so we're not going to find the equation of a line by hand. We're going to use R to find the equation. But if you're interested in finding the equation by hand, this is essentially a optimization problem that you learn about in Calculus 3 or even in linear algebra. You're basically finding the line that minimizes all of these little distances. All right, so in R, the command to get the least squares regression line is going to be LM. So LM stands for linear model, and then y squiggle x. Okay, so notice that the y goes first. If you're getting the answer wrong in this step, what probably happened is you got the order wrong. Y goes first, squiggle x. Okay, so let me switch over to R and show you how this works. Back in R, the way you get the least squares regression line is the command is LM, that stands for linear model, parentheses, and then y squiggle x. So what I mean by that is whatever name you picked for your y. Here our y was grade, so grade, squiggle, I call it squiggle, but it's actually, the proper name is I think called tilde. It should be in the upper left of your keyboard near the escape key. And then the name that you picked for x. So here our x's were absences. Make sure you spell everything correctly. If you're getting an error, it's probably because you spelled stuff wrong. Hit enter. And R is going to spit out the two special numbers, the two important numbers for a line. One of these is the y-intercept and the other one is the slope. The first number, it's called intercept, that's the y-intercept. And then the other number, the negative 4.213, is the slope. So let me go back and write these down. What I mean by compute the least squares regression line is I want the y equals mx plus b equation. So I want this equation, but replace the m with the slope and replace the b with the y-intercept. So our least squares regression line is going to be y equals, the slope was, I think we said was negative 4.213. X plus the y-intercept. The y-intercept, I think we said was 107.160. And that's the equation of the least squares regression line. Okay, the next thing it says here, the AB line command, that's going to be optional. I say it's optional because it works on regular R and it works on RStudio Cloud, but it doesn't work on the online R console. So if you're using the online R console, don't worry about the AB line. What this does is it actually plots the line. Let me actually show you what it looks like. To use the AB line command, you need to plot the scatter plot up. If you accidentally closed it already, that's okay. Just make a new one. The command, remember, is going to be plot, P-L-O-T, parentheses, and then whatever name you pick for your x, comma, whatever name you pick for your y. Our x here was absences, comma, our y was grade. And once you have your scatter plot, to get the least squares regression line on the picture, the command is AB line, parentheses, and then you're going to type in the intercept, the y-intercept, comma, the slope. The y-intercept we said was 107.160, comma, the slope was that negative 4.213. And as you can see, it draws in the least squares regression line. So this part is totally optional. It doesn't work on the online R console. So if you're using the online R console, just skip this step. But if you're on regular R or RStudio Cloud, this is just a nice way to check and make sure that everything looks correct. If for some reason the line doesn't fit your data, what probably happened was when you did the LM command, you had the X and Y swapped, right? It's always the Y squiggle the X. Now that we have the equation, we can answer some questions. Part C, what is the slope of the least squares regression line including units? The slope we said was the number that's multiplying the x, the coefficient of the x, which is negative 4.213. Typically, back in algebra, when we talk about slope, it's we think of it as a fraction. So I'm going to force this to be a fraction by putting it over 1. And then, what are the units here? What are the units on top and what are the units on bottom? So our two choices are absences and grade. So what goes on top and what goes on bottom? Remember, back in algebra, you may have learned slope as rise over run. Rise meaning up or down, and run meaning left or right. So up top should be our up-down units. Up-down would be y, and our y units are grade. That means that the up top, the units are going to be grade. Run means left or right. Left-right units are our x. Our x units are absences. So for slope, the top's going to be our y units, the bottom will be our x units. And then interpret the meaning of the slope in this situation. The slope tells us the rate of change. It tells us if one variable changes, how the other one changes. So one way to interpret this is to say, I'm going to start with the bottom. If the absences positive 1 means increases by 1. The grade, it's negative, so I'm going to say it decreases. If that negative wasn't there, and that was a positive 4.213, you would say increases. But because it's negative, it's going to be decreases by 4.213. Okay, so what the slope is telling us is that if the absences go up by 1, the grade goes down or decreases by 4.213. Maybe a better way to say this in English would be to say, if it's for every absence that a student has, their grade decreases by 4.213. Okay, but you can always write it in this way. Part D, predict the expected grade for a student with 10 absences. We're going to take this 10 and plug it into our equation. The question is, do we plug it into the x or do we plug it into the y? So this is absences. Which variable is absences, x or y? X. So 10 absences should go in for the x. Okay, plug this into our calculator. Negative 4.213 times 10 plus 107.160. 65.03. All right, so let's take a look at our picture and make sure that makes sense. For a student with 10 absences, we expect the answer to be somewhere here, right, if it's going to match the pattern. which is around 65. Okay, that looks correct. Part E, should the line be used to predict the grade for a student with 30 absences? Why? Notice that our original data was from 1 to 15 absences, right? 30 absences would be way outside of our data. So typically, you don't want to use the equation for something that's way outside of our data because it could be inaccurate. So this is going to be a no. And I'm not going to write why, but why is because 30 is way outside of our original data. If you try to plug in 30 into our equation, I think you'll find that you get a negative score, which doesn't make sense in this case. Let's talk about some terminology. Correlation. Two variables are said to be correlated if they are related in a predictable way. And what I mean by this is that one variable can be used to predict the other. And we saw this in the first example. In the first example, we saw that absences and grade were related in the way where we can predict a student who had 10 absences would have a grade of somewhere between about 65, right? So absences and grade are correlated. And there are several different types of correlation. In linear correlation, the data follows a pattern. That can be described by a line. Right? The word line appears in the word linear. So this is the main type that we're going to be talking about in this class. And example 1 is an example of a linear correlation. Right here, the data follows a pattern, and it's a line. A nonlinear correlation, the data follows a pattern, but it's nonlinear, so it's not a line. But it is not a line. And let me show you an example of a nonlinear correlation. Okay, data follows a pattern, but that's not a line. For those of you who remember from algebra, that's a parabola, which is the graph of a quadratic equation. So this would be called a quadratic correlation. Some other terminology, positive correlation. Positive correlation is where if one variable increases, the other also increases. Visually on the graph, this looks like the graph goes upward from left to right. For example, something like that, right? The graph is going upward. So this is an example of a linear correlation because it looks like a line that's positive because it's going upward. Okay, that's an example of a positive correlation that's not a line. So this is a nonlinear correlation that's positive. Negative correlation means that if one variable increases, the other decreases. Okay, some pictures here. Graphically, a negative correlation just means that your graph goes downward from left to right. Okay, that's a negative correlation that's linear. And that's a negative correlation that's nonlinear. Okay, let's practice using this new vocabulary. For each of the following pairs of variables, determine whether the association is a positive correlation, negative correlation, or no correlation. Part A, age of a child and the height of a child. As the age of a child increases, do we expect the height to increase or decrease? So as the child gets older, do we expect their height to increase or decrease? Probably increase, right? Because as a child gets older, we expect them to get taller. So because of that, this is going to be positive. Because if one variable increases, we expect the other one to also increase. Part B, weight of a vehicle and the miles per gallon, or the fuel efficiency. As the weight of a vehicle goes up, do we expect the efficiency to go up or down? Probably down, right? Because a heavier vehicle is less efficient. So as the weight of a vehicle goes up, the other variable goes down. So this is negative. Part C, score on the SAT and college GPA. So as the score on the SAT goes up, do we expect, so if a student scores higher on the SAT, do we expect that student to have a higher or a lower college GPA? Probably higher. So this is probably positive. I put a question mark there because these days colleges are actually finding that the SAT is not a good predictor of how well a student's going to do in college. So I would maybe even say now that this is no correlation. So much so that some colleges are no longer requiring the SAT. Okay, next thing I want to talk about is the correlation coefficient. So the symbol is R, and this is a number that's going to measure the strength and direction of a linear correlation. And what I want to do here is just let's stare at these pictures for a little bit. Notice that these three pictures up here, right? These are these positive or negative correlations? The picture's going upward, right? These are all positive correlations. Notice that the R, this is R of 1, R of 0.9, R of 0.4. So these are positive correlations. Notice that the R is positive. These three pictures, they're going downward. So these are all negative correlations. The R for these pictures are negative 1, negative 0.9, negative 0.4. So these are negative correlations, and notice that the R is negative. So that's what I mean by the direction of the linear correlation. So R, if it's positive, that's an indication that the correlation is positive. If the R is negative, that's an indication that the correlation is negative. And then what about the strength? So notice that this is a perfect line, and this is a perfect line. The R here is 1, R here is negative 1. Okay? This looks more like a line than this. The R here is 0.9, the R here is 0.4. So the closer you are to a perfect line, the closer you are to either 1 or negative 1. So 1 and negative 1 are perfect lines. 1 is a perfect line in the positive direction. Negative 1 is a perfect line in the negative direction. And then the closer you are to either one of those, the closer you are to a line. And then this picture looks nothing like a line, and the R is 0. Okay, so let's summarize what we just observed. R is a number that's always going to be between negative 1 and 1. Okay. If your R is positive, that indicates that we have a positive correlation. So anything on this side is a positive correlation. Anything that's negative is a negative correlation. R of 1 and negative 1, these are our perfect lines. And an R of 0 looks nothing like a line. So an R of 0 indicates that there's no correlation. I should say no linear correlation. And the closer you are to 1 or negative 1, the more like a line your data looks. I want to emphasize that R only measures the strength of a linear correlation. In other words, it only tells you how close to a line your data looks. So here, this picture, the data looks like it doesn't follow a pattern at all, right? It looks nothing like a line. Here, R would be 0. What about this picture? Here, the data does look like it follows a pattern, but even here, R would be 0. Even though it follows a pattern, the pattern looks nothing like a line. So even for this picture, R would still be 0. So just because you're getting a R of 0 doesn't mean that the data doesn't follow a pattern at all. It just means that it doesn't follow a line, right? So even if you have a 0, it could mean that the data still is correlated, right? It still follows a pattern that's predictable, but it just might not be a line. All right, let's take a look at this example. So this is a matching example. We have some scatter plots, and what I want to do is match the scatter plot with the R. All right, so let's start with these first 3 R's, right? R of 1, 0.9, and 0.65. So those are positive, which means they should go with pictures that are going upward, right? Positive correlation. Which pictures go upward? These 2 pictures, right? Those are the only pictures that go upward. And notice that we don't have any pictures going upward that are perfect lines. So R of 1 means it's a perfect line. So that means that we're not going to be using R equals 1 at all. Okay, so there's no R equals 1. Now, of these 2, 0.9, 0.65. 0.9 is closer to 1, which means it should go with the picture that looks more like a line. Which of these pictures looks more like a line? This picture, right? This picture, the dots are a little bit more spread out. This picture, they're more closely on a line. This picture will be R equals 0.9, which means this picture would have to be R equals 0.65. Okay, so we have these 2 done. The next 3 here, negative 1, negative 0.9, negative 0.50. So these are all negative, so these should go with pictures that are negative correlation, in other words, pictures that go downward. So this picture, this picture, this picture, okay, these 3 pictures. Negative 1 means it's a perfect line, which means it should go with this picture. So this is a negative 1. And then negative 0.9, negative 0.5. Which of these pictures looks more like a line? This picture, right? So the closer you are to a line, we're on the negative side now, right? Closer you are to a line, the closer you should be to negative 1. So this one looks more like a line. Negative 0.90 is closer to negative 1. So this one would have to be negative 0.9. Which means this one is negative 0.50. And then R equals 0 means that it looks nothing like a line. This scatter plot looks nothing like a line. This would be R equals 0. How do we actually find the correlation coefficient R? There is a way to do it by hand, which we're not going to do, but let me just write down the formula to show you why you don't want to do it by hand. To do it by hand, the formula is this. Looks like a pain. It is a pain. So we're not going to do it by hand. We're going to use R. The command in R is going to be core.test, whatever you called your X, comma, whatever you called your Y. Okay, so let me switch over to R and then find the correlation coefficient. To find the correlation coefficient, the command is core.test, cor.test, T-E-S-T, parentheses, and then whatever you named your X variable, in our case here it was absences, comma, whatever you named your Y. In this case it's grade. And before I hit enter, let's go back and look at our scatter plot here. Is this a positive correlation or a negative correlation? It's going downward, so it's negative correlation. So I expect the correlation coefficient to be negative. And also the points look very much like a line, right? It looks very close to a line. So I do expect a correlation coefficient that is close to negative 1. Okay, so let's go ahead and hit enter here. And the correlation coefficient is the number at the very bottom, this negative 0.961. Okay, it is negative, like I expected, and it is pretty close to negative 1, like I expected. Continuing with example 1 here, the correlation coefficient that we just found was negative 0.961, so round to 3 decimal places. And it turns out that if you take this number, this R that we just found, and squared it, you get a number called the coefficient of determination, R squared. So if I take the R that I just found and squared it, we get, make sure you use the parentheses. And we get 0.924. Anytime you square something, a number, you should always get a positive number, right? So your R squared should never be negative. If you get a negative, it's probably because you forgot the parentheses. Now, this number R squared has a nice interpretation. And let me write down what the interpretation is, and then I'll explain what it means. So we're going to convert this R squared to a percent. So 0.924 as a percent is 92.4%. Okay, so I want that. 92.4% of the variation in and you're going to write the Y variable right here. Our Y variable here was which one? Absences or grade? It was grade. So 92.4% of the variation in grade can be explained by the variation in, and then you're going to fill in your X variable here. Our X variable was absences. And that's the interpretation that I want you to write for all of these. Convert the R squared to a percent of the variation in fill in your Y variable can be explained by the variation in fill in your X variable. Now, what does this mean? So there's many things that can affect a student's grades other than absences, right? Absences is only one thing that could affect a student's grades, but other things that could affect a student's grades. How much the student works during the week, right? Because that would affect how much time they can spend studying, which would affect their grade. quality of instructor, right? That could affect the student's grades. So of all those things that could affect the student's grades, we're saying here that absences account for 92.4% of the effect. Hypothesis test for linear correlation. Can you conclude that there's a linear correlation between the number of absences and the grade of a student? We said that this picture is no correlation at all. And this picture is a perfect linear correlation. Question is, where is that dividing line? How close to a line does the data have to be for us to say that it's a linear correlation? And there is no one dividing line. We have to decide using a hypothesis test. So in our typical hypothesis test, we had like 6 parts. Part A is the null and alternative hypotheses. The H0 and H1 for a hypothesis test for linear correlation is going to be, the H0 is going to say, and that symbol, that looks like a P, it's not a P, it's a Greek letter rho. On your lab, I'm going to use rho instead of the symbol because the symbol looks like a P. So it's saying rho equals 0. Rho is the Greek letter for R. So you can think of this as R, right? H0 is saying that R is 0. In other words, we're saying that there's no correlation. H1 is saying that rho is not equal to 0. In other words, it's one of these other pictures, which is saying that there is some correlation. Part B and C, we're actually going to not do for a hypothesis test for linear correlation. Part D, the p-value, we are going to do, but there's nothing to do because we already did it. If you go back to when we did the core.test, up at the top, there is a place that says p-value. That's the p-value. So our p-value here is 0.001. Rounded to 3 decimal places, it would be 0.001. Okay, our p-value is 0.001. And then part E we'll do, which is the reject or don't reject, H0. Same thing as before. We're going to look at our p-value and compare it with our alpha and see if it's less than. Our p-value is 0.001. Our alpha in this case was 0.01. Question is the p-value less than the alpha? If you need to, add zeros to make it match the number of decimal places. Our p-value has 3 decimal places. Our alpha currently only has 2, so let's add a 0. This is really just saying, is 1 less than 10? Yes. All right, so it is less, which means we do reject. And then part F, the sentence. At alpha equals our state your significance level. At alpha equals 0.01 significance level. There is or is not enough evidence because we did reject. There is enough evidence. To conclude that, can you conclude that there's a linear correlation between the number of absences and the grade of a student? There is enough evidence to conclude that there is a linear correlation between the number of absences and the grade of a student. Let's do an example all the way through. Example 2. The foot length and vocabulary size was measured for a sample of children. First column is our x, second column is our y. Part A, construct a scatter plot. So we have to enter this data into R. Let me use the online R console for this one, just to show you what it looks like. Here's the online R console. First thing we need to do is enter the data. Our first column is foot length, so you can name it, say, foot. Or if you want to be lazy, you can also just name it x. So let's be lazy on this one and call it just x. X equals C parentheses. And then type out the data separated by commas. So our foot length for x was 2, 5, 9, 6, 8, 8. Second column is vocabulary size. You can name it vocabulary, or if you want to be lazy, you can just call it y. I'm going to be lazy here and call it y equals C parentheses, and then enter the data separated by commas. Here's going to be 0, 80, 124, 53, 103, 158. And then to make the scatter plot, the command is plot, P-L-O-T, P-L-O-T, and then whatever you named x and whatever you name the y. Here, since we call it x and y, it's just going to be x, y. And that's our scatter plot. So it looks like it's going upward, so this is a positive correlation, and it does look like it's following a line. So part A is good. Part B, compute and plot the least squares regression line. The command in R here is going to be LM. LM stands for linear model. And remember, the order here is y first. So it's y, squiggle, x. All right, so let's go over to R. Back to the R console, so you might have to click on R console. Command was LM, parentheses, and then whatever you name the y, squiggle whatever you name the x. Here, since we call it x and y, it's just going to be y, squiggle, x. So squiggle is the symbol in the upper left of your keyboard. And R spits out the two important numbers for a line, the y-intercept and the slope. The first number, labeled intercept, is the y-intercept. The second number is the slope. So compute means write down the y equals mx plus b equation, but put the slope in for m and put the y-intercept in for b. So our equation is y equals, the slope is the second number, it was 19.24. Okay, don't forget the x. Plus the y-intercept was the first number, negative 35.52. Okay, you can leave it like that, but a better way to write plus negative is to say minus. So let me clean that up. So 19.24x minus 35.52. The plot part, if you're using regular R or RStudio Cloud, you can plot the line by using AB line. But on the online R console, that part doesn't work, so we will skip the plot part. Part C, what is the slope? The slope is the number that's multiplying the x, the coefficient of the x, which is the 19.24. And typically slope, we want this as a fraction, so we're going to force this to be a fraction by putting it over 1. I also want the units. Okay, our units here are either going to be vocabulary size or foot length. What goes on top and what goes on bottom. It's always going to be the y units over the x units. So our y units here are vocab size. I'm just going to call it vocab. So that's the y units over the x units, which is foot length. You can also say number of words, since that's actually the units for the y. And then for the bottom, it's inches. Okay, y units over x units, and the reason is because slope is rise over run. Rise is the up-down, which is the y, and run is left-right, which is the x. And then interpret the meaning of the slope in this situation. Okay. The interpretation is going to be if the foot length increases, And I say increases here because that's a positive 1. Increases by 1 what? 1 inch. The vocabulary size, increases or decreases. This is a positive 19.24, so it increases by 19.24 words. If the foot length increases by 1 inch, the vocabulary size increases by 19.24 words. Part D. Predict the vocabulary size of a child with a foot length of 7 inches. This just is asking you to take the 7 and plug it into the equation that you found in Part B. Where does it go? Does it go in for X or does it go in for Y? This is a foot length. Foot length is X, so we're going to plug it in for X. 19.24. Put the 7 in for X. That's 19.24 times 7 minus 35.52. 99.16. 99.16 what? This is supposed to be a vocabulary size, so words. Part E, compute the correlation coefficient R. So this, you need to go back into R and do core.tests. And it's going to be X comma Y. All right, so let's go back to R. Core.tests, parentheses X comma Y, or whatever you named your X and whatever you name your Y. But here, since we named it X and Y, it's just going to be X comma Y. Okay. Correlation coefficient is the last number, 0.894. Correlation coefficient is 0.894. Part F, compute the correlation or coefficient of determination R squared. That's just asking you to take the R that you found and square it. Okay. Parentheses 0.894 squared. 0.799. So round everything to 3 decimal places. Because we're squaring things, you should always end up with a positive answer. Okay, so if you don't end up with a positive answer, it's probably because you forgot the parentheses. And then the interpretation. Convert this to a percent. That's 79.9%. So 79.9% of the variation in. And you're going to write down the Y variable here. 79.9% of the variation in vocabulary size. We'll write vocab size. Can be explained by the variation in and you're going to state your X variable here. Our X variable was foot length. So 79.9% of the variation in vocabulary size can be explained by the variation in foot length. And what this means is that there's many variables that could affect a child's vocabulary size, right, other than foot length. But what we're saying here is that foot length accounts for 79.9% of the effect. Part G. Can you conclude that there's a linear correlation between foot length and vocabulary size? This is the hypothesis test. For the hypothesis test for a test for linear correlation, I'm only going to ask for the H0, H1, The H0 for a test for linear correlation is going to say rho equals 0. Okay, this is the Greek letter rho. H1 is going to say rho not equal to 0. Think of these rows as R's. R equals 0, that means that there's no correlation at all. R not equal to 0 means that there's some correlation. And then I'm going to ask for the p-value. And the p-value we actually already have when we did the core dot test. So if we go back to R, it says p-value is 0.016. P-value is 0.016. And then do we reject or don't reject H0? So to decide, take your p-value and see if it's less than the alpha. Our p-value is 0.016. Alpha for this problem is 0.05. If you need to, add some zeros so that it matches the number of decimal places. Now let me add on a 0 to the alpha here. This is really just saying 16 versus 50. P-value is less than the alpha, so this is going to be a reject. And then finally, our sentence. State your significance level at alpha equals 0.05. Significance level. There is or is not enough evidence because we did reject. There is enough evidence. To conclude what? Can you conclude that there is a linear correlation between foot length and vocabulary size? There is enough evidence to conclude that there is a linear correlation between foot length and vocabulary size. Okay, so we came to the conclusion that there is a linear correlation between foot length and vocabulary size. So there is some relationship between foot length and vocabulary size. So it's important to note that correlation does not equal causation. So just because two variables are correlated doesn't mean that one directly causes the other, right? Foot length doesn't cause vocabulary size, right? There could be a lurking variable, another variable that's actually a better explanation for the cause, right? So foot length and vocabulary size, they're both going up at the same time, right? So if foot length goes up, vocabulary size goes up. But a better explanation for what's happening here would be what? Probably age, right? So as a child gets older, right, their foot length gets longer and their vocabulary size gets bigger, right? So a better explanation might be age. Just so happens that foot length and vocabulary size both go up with age. And then another example, more famous example is this one. So here we have ice cream sold and the murder rate. Based on the scatter plot here, it looks like ice cream and murder is correlated. It does kind of look like a line. But does ice cream cause murder? Can't be, right? That's ridiculous. So there's some lurking variable. There could be some other lurking variable that's a better explanation for what's going on here. And an example of a lurking variable here that might be a better explanation would be, say, the weather outside. Right? In warmer weather, there might be more crime, and in warmer weather, more ice cream might be sold. So a better explanation here, a lurking variable, could be the outside weather. All right, that's it for chapter 4. Have a great day, and I will talk to you later.